Hello, it's Keith here, and this is lesson 19 of the platform-specific series of my 6502 assembly programming tutorials. We're going to be looking at how to define colours on the Atari Lynx this week. Now, compared to other weeks, this week's going to be quite different because in the past we've been having to use lookup tables because our systems haven't been capable of defining colours in an RGB format. However, fortunately, thanks to the Lynx's excellent graphics capabilities, we can do that this week. We can define our colour definitions in a 1 nibble per channel definition, and this will allow us a nice set of reds, green and blues to make up our colour with. Now, in these tutorials, if you didn't catch last week, we use a common format on all our systems. We actually use a single nibble per channel, just like on the Atari Lynx. However, we do use a different order. Now, the Atari Lynx uses green, blue and red. However, in our tutorials, we use green, red and blue. Now, obviously, that's going to need swapping around, but I designed this layout based on the CPC Plus a long time ago. It's common across all the tutorials, so that's just the way it is. Not ideal for the Lynx, obviously, but no real problem. Now, when it comes to defining a colour on the Lynx, we have two sets of 15 ports. The Lynx has 16 colours on screen and it uses the same colours for sprites and for bitmaps. So there's only one set of colours for everything. We define the green colour by writing a byte to the FDA0 to FDAF range, and then we write the matching blue and red components of the colour to FDB0 to FDBF. So for example, FDAO and FDBO together will make up the red, green and blue component of colour 0, and we just move along for the other colours, as we'll see in the code later on. So enough talk of that, let's actually see the code running today. So here's the tutorial example. We've seen it in the past. Here's our Chibico character, and Chibico has white skin, purple hair and this kind of cyan clothing and shoes here. So we've also got black background, of course, and that's the four colours we're going to be defining today. So let's have a look at the code that's actually doing that work for us. Now, we're using this palette definition just here, and it's these four colours we want to take a look at. Now, you can see here that the background colour is 0, and because we're using 1 nibble per channel here, with the top nibble unused, you can see these hexadecimal numbers here will give us an idea of the colour that we're building up. So you can see here we've got 3 zeros here for green, red and blue, which of course makes black, which is the background. Colour 1 is using a partial amount of red and blue. That's going to basically make a mid-purple, so that's our hair. And then we've got the cyan here, which has got slightly less green than blue, but yeah, we can't really tell that. So that's the cyan colour. And finally, colour 4 is the white here. And that's the face. So those are the colours that we're using today. So we're using this palette definition. So how do we actually send it to the hardware? Well, we've got this little loop here. What we're doing is we're loading DE, ZDE, which is 0-page entries with the address of the palette. We're then loading in 2 bytes from the palette because each colour definition is defined by a single word. And we're storing them in ZHZL in the 0-page again. We're then setting the accumulator to the colour number. So colour 0 would be the first colour and colour 1 would be the second one. So we're setting A to 0, 1, 2, 3, 4, etc. And then we're calling this set palette function. And it's that set palette function we'll be looking at today because that's what's setting up our colours for us. And here it is. So let's have a look at it. Well, what are we doing? Well, the first thing we're doing is we're just backing up the accumulator quickly, and that's so we can push all of the registers onto the stack using this push all macro. This is just so that any counters are the same after we've finished the function. And then what we do is we get the accumulator back from this ZAS temporary entry in the 0-page here. And then once we've got that, we're going to store our data. Now, the first thing we're going to do is we're going to write the green component. Now, the green component is actually in the correct position. Now, our definition for these tutorials is green, red, blue, but the definition for the Lynx is green, blue, red. But the green is in the right place. So all we do is we write it straight over to ZBC, which we've defined here as pointing to FDA0, which is the first part of our definition. Remember this part here, FDA0 to FDAF. Now, you will notice here that we're offsetting by the Y register here, and we've moved the value of the entry we want to change into the Y register just here. So this is effectively storing the green component into the hardware. Now we've finished writing the green components, so next we need to write the red and blue components. Now, of course, they need to be written to a different address. The top byte is the same FD, but instead of A0, we need to write to B0. So we're just changing ZC here. And then what we do next is we load in the red and blue components. Now, our source definition is in red nibble first, blue nibble second, but we need it the opposite way around for the hardware. So what we're doing here is we're using this swap nibbles function, which you can see just here, and this does a combination of these 3 commands, which will shift 2 bits around, and we do it twice to effectively swap the 2 nibbles over. And now we've got the colours in the right format, so all we do is we store to the second address FDB0, offset again by Y, which is still our palette entry, and this has effectively set the palette for the colour we wanted to change. And that's really all there is to it. It's very straightforward on the Atari Lynx because it's using 1 nibble per colour channel, just like our definitions in these tutorials do. So there we go, that's all it takes really. Now, as always, I mean, if you only wanted to support the Lynx, then maybe you would want to write your own native palette definition code. I did it in this way because I find it a lot easier when working on a lot of different systems with things like Grime 6502. This was the code I used, and it allows me to use a single palette definition and get all of the games looking as close as possible without tweaking different palettes for different systems. Another benefit is with the Chibi Akuma's game, which was a Z80 based game, but it still applies. I wrote code to do fading routines, and I just modified the nibbles of the palette definitions and then resent the palette definitions to the hardware. If you use code like this, then you can write 1 fading routine and it will work commonly on all of your systems. So as I say, if you're looking for a single platform game, then this may not be appropriate, but for a multi-platform game, I think it's a really good move to make. Anyway, I hope you've enjoyed this. Please like and subscribe and stick with me if you like the Atari Lynx, because we're going to be looking at the sprites later on. So this isn't the last we're going to see of the graphics on the Atari Lynx. Anyway, thanks for watching today, and goodbye.